This is the third and final lecture on parallel imaging. In this lecture we're going to talk about computing the grappa weights, then we'll talk about spirit iterative parallel imaging reconstruction, and then we'll give an intro to compressed sensing, which will be the topic of next lecture. So if you recall from the last lecture that the synthesized data in a grappa reconstruction at a given, for a given coil L as a function of k-space position kx and ky is the sum of the weighted data where the weights are given by A, I, J, K, and the data is the data from all the other coils in a small neighborhood around the target location that we want to synthesize. So here's a graphical depiction of this. Let's say that we're trying to synthesize the data for coil 1, then we take data from that coil's sample data from that coil, and we weight it. For example, this would be A111, and we would also multiply. This would be the weight A11 multiplied by the data point here in coil 1's own k-space data, but we would also add to that summation data point weighted data from coil L, all the other coils including coil L, where they also have their own weights. So this guy would be -1, 1, comma L. So here the first two indices of the A subscripts refer to the offset in kx and ky respectively, and the last index refers to coils. Okay, so we talked about a lot about how this equation would work, how the synthesis would work, but we didn't talk about how to actually find these coefficients A, I, J, K. So what we do is we use auto-calibration. And specifically, we assume that there is a region of k-space that is fully sampled. Which implies that we have samples of what the above equation should produce, right? If we have a region where we already have the synthesized data, then we have the left-hand side of the equation, and we have the data from which these points were synthesized, so we should be able to invert a system of equations to get the weights. And so we can invert this to get the weights. Now the calibration region must be bigger than the grappa kernel or operator. Typically it's much bigger, so that you have at least as many linear equations, if not many more linear equations, as you do AIJK coefficients. Specifically, you want to take the calibration region to be the middle of k-space, since that's where you have all your the most SNR. So as an example, let's say we have this is depicting a fully sampled region of k-space, and what we're going to do here is we're going to slide a window around it here, and at each location we are going to take each sample, multiply it by the weight, and synthesize the other sample. But because we already have the samples, we already have the synthesized samples, we can invert this to figure out what the weights are. So each centering of the operator gives one equation here. And so here a 3x3 kernel operator, and then we have a 5x5 calibration area, which will give 3 times 3 equals 9 equations. Okay, so that is exactly as many as we need. We have 9 weights, 3 times 3 weights, and we need 9 equations at least to get those weights. We can write these equations as a matrix vector equation, right? It's a linear system of equations, so we can write it as in matrix vector form, where the calibration data, M sub L, is equal to the neighborhood samples, the samples in the neighborhood, across all coils, collected across all coils, times the grappa coefficients that we're trying to solve for, A sub L. So again, in this system, the data here is known and the neighborhood samples are known, and we're trying to figure out what are the weights that when we multiply them by the samples in the neighborhood give us the calibration data. So then the weights, this system of equations can be inverted to get a set of weights or coefficients equal to a regularized pseudo-inverse MA Hermitian times ML. Now note here that M sub A is going to be a matrix, M sub L is going to be a vector. Right? This is going to be a tall, skinny matrix which has the number of columns as the number of coefficients. In this system of equations up here, you would have 9 coefficients, right? So this would be a vector of length 9, and this would be a matrix of with 9 columns, and then let's see, and then also 9 rows. And so what we have here is a regularized pseudo-inverse of this M sub A matrix, where we are adding, the regularization refers to the fact that we add this lambda times identity matrix here to improve the conditioning of the inverse and avoid noise amplification. So again, here lambda is an optional regularization parameter which improves the invertibility of the matrix and downweights the coefficients a little bit. An interesting feature of this problem, so you note that the data matrix M sub A is formed from the data itself, which is noisy. Adding noise to a matrix can improve its invertibility, which means that low SNR data can actually, in some cases, improve grappa operator estimation and consequently grappa reconstruction. Or conversely, too high of SNR can lead to erroneous operators. Of course, this can be mitigated by selecting lambda appropriately also, but many users naively set lambda equal to 0. Okay, so let's put this all together. In the grappa algorithm, we first compute the grappa operator from the calibration region. Then we compute the missing data from the grappa weights. Then we recon the individual coil images. And finally, we combine those coil images. So there's no unfolding to do here as there is in sense. After we fill in the missing data in K-space, we already have unaliased full field of view images for every coil. So the last parallel imaging reconstruction we'll talk about is spirit. So to motivate the spirit algorithm, we should touch on a few issues with grappa. So the first is how to determine the calibration region size. The second is, how big should the kernel be? These are really unintuitive parameters to set because you're working with the Fourier transforms of the coil sensitivities. If you truncate them too much, then you're not going to capture enough variation far away from the point that you're trying to synthesize. And if you make it too large, then that gives you a larger. If you make it too large, then that requires a lot more computation, requires a much larger calibration region. The other problem with it, though, that Spirit really addresses is sample geometry dependence. Okay, so the grappa weights depend on which samples are acquired and which ones are estimated. So here in this illustration, I'm using X's to denote acquired samples and circles to denote samples that are to be estimated. Sorry. So this geometry is simple for when we're just skipping lines, right? Because we just take the same kernel and we slide it around. Let's say that we're estimating this point here. Well, it uses those neighbors there. And then we just shift it along when we want to get to the next point that we're synthesizing, right? You can use the same structure, the same indexing, everything. So the same weights work everywhere. But it's harder when we have, for example, 2x2 acceleration, as you might have for 3D imaging where you have two phase-encoded dimensions. So then to accelerate your scan, you would undersample in 2 dimensions. So in this case, for example, you would want to synthesize this point from these guys, but then you move over 1 on this side, and okay, you've only got 2 samples that are really close by. Likewise, if you're trying to synthesize here, you've also got only 2 samples that are close by. So these kernels, this would require the construction of 3 different kernels to get this, and it's not clear how well it would work. So overall, each geometry of missing with respect to known samples has its own set of weights, and it rapidly gets confusing trying to keep track of all these different geometries. For irregular sampling, such as non-Cartesian sampling or random sampling, as is used in compressed sensing, it becomes really unmanageable. So SPIRIT is based on an alternative perspective on how we apply the weights. So let's assume, take a step back here and assume that you know the final reconstruction already, right? You've already reconstructed the final full K-spaces, and you're trying to estimate a sample from its neighbors using the grappa kernel. Let's just say that we have all the data, we knock out one sample, and we're trying to estimate that sample from its neighbors using the grappa kernel. Okay, so we have all the neighbors here, and we're trying to estimate this one point. Right, and so we have this guy, and that's synthesized from coil 1, coil 2, up to coil L. Intuitively, this estimate that we get at this point should equal the value that you already have at that point, right? That is, in other words, applying the grappa operator should do nothing to this data point when it's applied to the correct reconstruction. And so that really is the whole basis of SPIRIT. So in other words, the final reconstruction should be consistent with the full grappa operator. And this is the basic idea of SPIRIT. Okay, so here's the overall algorithm / basic idea. So first what you do is you calibrate on the entire neighborhood. Then you fill in the known data. And set all the other data to 0. Then you apply the kernel to estimate all the data, the known and the unknown data. Then you replace or restore the known data in its locations because we trust that data. And you iterate steps 3 and 4 until the data stops changing. So this is another example of a POX algorithm, a projection onto convex sets algorithms, where here we have 2 convex sets. One is the set of data that is consistent with the kernel. By that I mean K-space data synthesized and unsynthesized. Or sorry, yeah, synthesized and known ahead of time. Consistent with the kernel. And the other set is, the set of data that matches the acquired data. Now the cool thing about this is that the same operator or weights, you can use the same operator or weights for any geometry or sampling pattern. right? So you can use it here. You can use it here. And you can use it here. Right? You're going to have some samples over there as well, presumably. And then the zero value, and as you run this, the zero values slowly fill in. So the advantages to this is that you only have to build one set of weights. It works for any sample geometry. And you effectively are using a little bit larger kernel, which is often good. The disadvantage is that it's iterative, which translates to computationally slow. And in the end, what you end up with is just as in conventional grappa, you end up with fully sampled coils k-space data, and you can combine them using any multi-coil combination method, just as in grappa. Okay, so now let's get into an introduction to compressed sensing. So this is a graphical illustration of the compressibility of medical images. So we acquire typically our full k-space data, then we reconstruct it into an image. Again, we haven't thrown anything away between these two steps typically, but then it turns out that usually we can compress a lot to reduce the size of the data down to a small number of small set of bits when we store it on a disk. So that is, medical images are compressible. And with negligible loss, a compressed image can have maybe 10% or even less data points than the full k-space data. So the question then is, why bother you ever collecting the other 90% of the data if we can compress it down to something so small? So this is a good quote here, that people get nervous when you start talking about throwing data away from a medical image, but if you never collected the data in the first place, well, that's a much better situation. Okay, so how can we get away with this, not collecting this data in the first place? Fundamentally, we want to undersample the data, but we know that this produces aliasing. So we need to be able to tell the signal apart from the aliasing. Right? We could remove aliasing if we could tell the signal apart from it. So let's consider parallel imaging. In parallel imaging, comparing the fully k-space data, the fully sampled image. If you undersample it, you get these coherent artifacts, right? You get these coherent aliases, which are direct copies of the original underlying object. So in parallel imaging, we know where the aliases go. And we know analytically what they will look like. We know in this particular case, if this is like an illustration of a factor 2 parallel imaging acceleration, we know that we're going to get exact copies of the underlying image. So to undo it, we need the coil sensitivities. Okay, so in this case that I've illustrated, we have uniform sampling at full field of view sampling, where our spacing between k-space locations that we sample is delta k, which gives us a field of view that is 1 over delta k, and our object has to fit within this region, right? If we have uniform undersampling, let's say that we accelerate by a factor of 2, then we have doubled the gap between the k-space points, so this is 2 delta k. And this results in the copies of the image brought in a factor of 2 closer. But another thing that we can do is random undersampling. Why should we necessarily have to space them uniformly? If we also do random undersampling at a factor of 2, where we have overall the same total number of samples, but now we are randomly choosing whether or not to save to collect a certain data point, well, then we're going to get a pattern that looks actually more like the full sampling case, right, in terms of which spikes are largest, but we're also going to get these kind of random looking smaller spikes, smaller copies of the image. Where here, this is the field of view again. So that's the two biggest spikes are still separated by field of view. So with random sampling, it turns out that aliasing looks like noise. And so it's easier to tell signal apart from aliases. So then the basic idea of compressed sensing is twofold. The first idea is to randomly undersample. You randomly undersample your data in k-space. That gives you noisy-looking aliases, and then you apply a denoising algorithm, essentially, to the image.